In this episode of Stemiverse, Marcus and I talk with Philip Mallon. Started at the age of 9, Philip built a radio crystal set, and this became the foundation for an interest in electronics. Philip's path has given him countless opportunities to learn and to teach during the last 40 years. As a cadet with the New South Wales Department of Public Works, he studied science and technology at the University of Sydney. This was followed by further studies in the UK and a master's degree in engineering science at the University of New South Wales. Philip applied his new knowledge in biomedical engineering to providing electromedical equipment for the new Westmead Hospital. He worked on the first electronic toll system for the Sydney Harbour Bridge and was a control systems engineer on the accelerated loading facility. Philip helped provide the first computer systems engineering labs at UTS, the University of Technology Sydney, and was employed there as both engineering manager and as an academic to provide both teaching and practical engineering skills for students. While at UTS, Philip was a director for Autism Australia, now called Aspect, and took an interest in supporting schools for autistic children. At the RTA, the Road and Traffic Authority in New South Wales, Philip was engaged in Intelligent Transport Systems project, including the flashing lights at all school zones in New South Wales, road safety projects, including the Lithgow Black Ice Detection Project, managed motorways, the new T-Way bus systems for Sydney, and structural health and security monitoring projects, including monitoring the Sydney Harbour Bridge for security threats. Now retired, Philip is an active maker and mentor to other makers at the University of the Third Age and various Sydney meetups including Osbury, Sydney Robotics and Coding and Hack Sounds. Philip's maker projects involve music, robotics, home automation, environmental monitoring, software engineering and electronics, and his interest in how people with disabilities such as autism and retired seniors can be creative as makers. Philip exhibited his maker projects at the Sydney Mini Maker Fair last year. He's an alpha tester for new Seed products, including ReSpeaker, and won 2 of their design competitions using ReSpeaker and WireLink. In the next hour or so, Marcus and I explore Philip's amazing engineering and learning experiences, and it was fascinating. This is Stemiverse episode 10. Welcome to Stemiverse, the podcast that helps educators become awesome at teaching STEM, be it at home or in the classroom. I'm Peter Dalmaris, and with my co-host Marcus Schappi, our mission is to bring you the experiences of educators, students and stakeholders who strive every day to make the teaching and learning of science, technology, engineering, mathematics and art better. Philip, thank you for joining us in this episode of Stemiverse. Really appreciated having the opportunity to talk to you. I'm here with Marcus, and we'd like to explore your educational background, especially in relation to STEM.
Thanks for the invite.
We planned this a while ago, so I'm very excited because we actually go back a while at UTS, even though back then, that's about 20 years ago, we didn't know about it. It's like our paths crossed again all this time later. So I'd like to start this interview by asking you to tell us a little bit about your background. So going back as far as you feel comfortable, tell us about perhaps when you remember yourself becoming interested in engineering, in science and education, and tell us about your story, how you got to where you are now.
Sure, certainly. My first project, Maker's project, was when I was 9 years old. And I did that with my dad and built a crystal set. So a radio crystal set was the thing you started off with in those days. Mm-hmm. And my father, he was selected because he had really excellent hearing, and he was selected to become detecting submarines in the Second World War. So they trained him to be a technician. He didn't have any background in that area, and he became interested in electricity, and the British Navy taught him how to maintain all the gear.
Wow.
So that he had to repair it.
Right.
So not only detect submarines, but he also had to keep them going, keep that technology going. And they gave him quite a thorough grounding. So he kept that interest alive.
So it was Second World War, right?
This was the Second World War. Yeah. So someone he was an upholsterer before that.
Right.
But he. So I sort of look at my origins of my interest. Probably goes back to that.
So it's the necessity, the wartime needs, got your father into this completely new thing for him, from being an upholsterer to now being somebody detecting submarines from sound and maintaining electronic equipment in a submarine.
Yes. So he had to know the first principles, and he would have his own gear to repair, but he then made things and involved me in that process when I was the age of 9 or so. So while we migrated to Australia, we didn't actually do much until I was about that age. Before then, we saved up for a house, and we didn't have much money for hobbies. But around about that stage, we started making things. A couple of years later, he gave me a kit. So there was a model railway system called Trains. They brought out the equivalent, an electronics equivalent, that allowed you to play with printed circuit boards, transistors, and I was able to actually put together radio receivers, super heterodyne receivers, and things like that at about the age of 12 or so.
So it's about in the 60s now, that'd be around early 60s?
1962 or so.
Did you have brothers or sisters?
Yeah, I have got one brother and one sister. They're not interested. They're totally medical.
Okay.
And I became interested in medicine too, and I didn't really know for a career, would I go for medicine or would I go for engineering? And I eventually combined the two of them. So I did biomedical engineering, which in my master's course, I specialised as much as possible in that area. So my early career was biomedical engineering.
So you come to Australia, you build gadgets like that with your father. And then you go through a normal school process, and then at some point you have to choose what you want to do with the rest of your life, and you had these two options. You could go towards the medical or the engineering option, and you decided to combine them. What was that back then? Because it must have been early days for such a discipline like a biomedical engineering. Yeah,
it was brand new, and I just happened to be the right person in the right place. So just starting university, I chose engineering because the state government had state scholarships.
Which university?
Sydney University. And the state scholarship gave you a full-time salary when you attended university. So if I did medicine, I would have to pay for everything. But with the state scholarship, they gave you employment and guaranteed work as soon as you graduated for 5 years.
Was it specifically for engineers?
Yeah.
They didn't have that same policy in any other discipline?
No, they had, the government architect employed architects, and they would have surveyors. So the state government had a lot of technical experts. Probably less today, but in those days they did everything themselves.
No outsourcing to the private sector back then, right? So the government would hire these people directly to build roads, bridges, whatever.
That's right, yeah. So they were government employees. And if you could remain a government employee for life, you could retire quite well.
Yes.
Good superannuation, all that. But it's all changed now. It's totally changed.
It's quite interesting that the scholarships that you get, basically you were an employee employed to study engineering back in the 60s.
Yes.
And how different that is now.
It was totally, when I went to university, we were the first students to use mini computers, which would actually boot up the computer. So we had total control. The previous generation actually just looked at computers behind a glass wall.
So they didn't even get time sharing?
They never actually got their hands on. So they put their cards in. We used to have decks of cards. Whereas we were actually bootstrapping it with paper tape and then using the computer to control. And when I got out of university and started my first job, they were beginning to use these mini computers, not just in banks, but they were beginning to use them in hospitals and all over the place. And nobody in the government knew anything about it. But I was lucky enough that I had some experience that I could actually tackle the first jobs in that area.
So tell us about having computers like that just first appearing, and obviously there's a big expensive things, you need a building for them. As a student, what was your relation with those machines and how were they used in this educational process back then? Were professors interested in using them as a teaching tool, or was it just part of the job? And
they were the first computers which were a component in a discipline of control engineering. So prior to that, control engineering was all about analog computers and feedback, PID, algorithms and all that sort of thing. And all of a sudden we had affordable computers which could be part of the control system. And that's how I got involved. In my undergrad, I specialised in control systems engineering. And prior to that, I did a degree in science. And that was also good because I actually got some hands-on in the physics laboratories right through the whole program at Sydney Uni. So I started off with a Bachelor of Science and then went on to complete with the Bachelor of Engineering at Sydney Uni. But what was really good was every single holiday I was able to get out and starting off in a workshop, hands-on, and doing stuff. Then installing things like air conditioners in hospitals, then working through testing things like the safety systems in hospitals. So I did all that as an undergrad for 5 years. So it was quite a good background.
Did you have some kind of mentorship as you're going through all that by yourself? So tell us a little bit about that experience, your mentors.
Yeah, I had a pretty free rein while I was at uni, so just like everyone else. But as soon as the exams finished, you went straight back into the government with full salary, and you were able to get like a 6-week apprenticeship in different sections in the government.
It's amazing. Do they do this anymore?
No, they don't do it anymore.
Okay.
But it did encourage me to think about that. And when just recently, before retirement, I was involved in a grad program for the RTA, which selected and then looked at how graduates in computer systems and electrical engineering could go through and get similar experiences, perhaps in a different way. They were graduates now, not undergraduates, but I was quite interested in that process of learning and the process of combining my different interests for the next generation of engineers.
So you get through uni, you finally graduate.
Yeah, I graduated, but I still wanted to have a continuous involvement in education. So I worked for the government architect and involved in equipping hospitals. That was the main thing. Selecting X-ray equipment and testing that. I tended to get towards the more complicated. The first thing I had to do was work out the safety systems in intensive care wards where people that had open heart surgery, they're quite vulnerable to micro amps of current. So I had to try and work out the earthing systems. They just introduced a brand new Australian standard, and that had to be then implemented in cardiovascular laboratories where people were having open heart surgery. So that was quite interesting.
Is that inside the medical theatre specifically, or even in the ward?
It's not in the ward, it's where they actually cut open the heart and insert electrodes and probes, so you no longer have the skin to protect you. So it means microamps of current, if there's any leakage current from an instrument, could actually cause a condition in the heart called fibrillation. And it didn't take much for that to happen.
So there were things like cauterizing equipment, that kind of thing? Or?
Yeah, it was mainly equipment that looked at ECG, or the electrocardiogram. So it was equipment, and a patient could actually be connected to quite a number of instruments. So it didn't take long before you got leakage currents. And we had to either go for a complete earthing system, as the British did, or go for a completely floating system with isolating transformers but monitoring the leakage current on either side. And we went for that solution.
Why?
Because if you could have two dangers. If you had any leakage current, you then fell back to like an earth condition. If you had the other system, a complete earth system, your circuit breakers would, and they now call them residual
current device. Yeah.
current devices.
RCDs, yeah.
Yeah, the RCDs. If you only had an RCD solution, you would interrupt the operation, and
Yes, not good.
that's not.
We got all this effort, generators and backups, so that
That's
you
right.
have the power.
Yes.
Great.
But we gave the surgeon a choice. They knew that there was a danger, but they could still continue. And,
Okay.
Yeah, so there was some monitoring going on, feedback, and they knew the risks involved in using electricity in that environment.
I wonder, Phil, like all these things that you were doing back at that time, they don't sound things that are mainstream, that there's a lot of people doing. So you're one of those people that has to figure out how to ground an operating theatre so that the patient is safe from those microamps. If there's no other people to ask advice, how do you go about figuring out what's the right thing to do? And remember that there was no internet back then either. You couldn't Google these things, right?
Yep.
So did you have some kind of process that would help you get through and answer a lot of these questions that you had as you...
Well, mainly interacting with other experts. So the people who knew more about it than me were the anaesthetists in the hospitals. And there was one particular anaesthetist who knew everything about engineering. So I learned...
So an engineering anaesthetist.
He used to take a screwdriver into the operating theatre,
Yeah,
and if
okay.
there's something wrong, he could actually fix
On the fly.
on the fly.
Just leave a patient and fix a machine, right, to save the patient.
And he actually he was like a mentor. He knew quite a lot about medicine and a lot about engineering. He eventually became CEO of Teletronics. So all the pacemakers and things like that, he was involved in exporting those to the world.
So people were your source of knowledge directly, right? And you call them your mentors. There was no Google. Pretty much books had not been written specifically on those topics.
Yep.
So you had to ask the right questions
Yep.
to people that you expected to have the knowledge. How far do you think that this same approach can be applied today? It seems to me that people would go to Google first and then ask people a question unless they can find the answer on Google. Do you think that Google has replaced the mentors?
I think engineering had a problem with being over-specialised, and in some ways working with a team of other experts, of mechanical, architects, doctors. As a team, you worked out the problem together and the solution together. Part of that problem was that you tended to only learn a little narrow discipline. So you relied on others and communicating them verbally. You had to go and talk to them and understand what their problems were.
Yeah. I also think that these are high-stakes situations that you're describing now. So operating theatres and wards, they're not things to be getting around with. So suppose that environment of being free to talk to others, explore problems from different dimensions, ask people of different disciplines, like the anaesthetist, for example, of their opinion, that would be a way to reduce risk and get to an answer that is a correct answer, right?
Yep.
Yeah.
I think I had a lucky break in working for the project manager of the Opera House. His next project was Westmead Hospital, and he gave me 10% of his budget. So this was the first time New South Wales in the last century had ever built a teaching hospital. And there was a lot of politics involved between the state and the federal government. Again, I was there at the right time, and the new government said, we're going to spend a lot of money on medicine, and we're going to change the balance, because all the teaching hospitals and all the health services were in the eastern suburbs. And here, there was a sudden explosion to try and redress that balance in the west. So Westmead Hospital was from nothing, from a speedway, became eventually Australia's largest hospital.
Yep.
And I was the I was only about 9 months out of uni at this stage, but I became the electromedical consultant. Again, I couldn't do it on my own. There was really a team of other people that I had to pull up to draw on. But it was quite exciting in terms of, well, the technology they were going to put in there, Australia had never done it before.
What were the new technologies?
Well, things like linear accelerators for cancer treatment. We had only things like, until recently, 6 MeV linear accelerators. So that the size of the microwave tube would be about that. And then all of a sudden we were going to go to 20 MeV. And facing problems like if you shot that to the concrete, you could transmute the elements within the concrete and cause radioactive. So
radioactivity on
they could become radioactive. And so they were building this hospital and they fast-tracked the whole thing. And they were putting things like the maternity block right on top of the linear accelerators.
Oh, great.
They had no idea what they were. Yeah. So I had to know, well, what was a linear accelerator? And should we buy technology like CAT scanners that were just being introduced for the first time? Should we buy them now? And they were becoming obsolete very, very quickly. So what was the best return on the investment for the state? So I got involved in some of those sort of things with doctors all banging on the door, everyone wanting this new technology.
The accelerator.
Yeah.
So in that kind of environment, do you think that you developed some sort of technique or philosophy in, first of all, how to learn? Because you really had to learn a lot of diverse topics and fast, right?
Yep.
And then how to also teach.
Yep.
Since I think you were the senior consultant, so you had to consult people, which is something similar to teaching, right? So I'd like you to talk a little bit about those two aspects, techniques you developed to learn quickly and then to teach others. And how do you think that eventually followed you into your academic years, a few years later in this story?
Two things. The first thing I did was to do a master's simultaneously when I was doing this. And the University of New South Wales, with their Masters of Engineering Science, was very flexible. So I could do a combination of things that I thought was more appropriate for me.
Was it a coursework master's or?
Yeah, it was coursework masters. So what I did was everything from ergonomics, because I was interested in how human beings interacted with technology. And they had some really good experts in that field.
What time frame? What years?
Oh, yeah, I dragged it on a bit. So I started in 1974, and I interrupted that program and went and did a Confederation of British Industry scholarship for 2 years. And it also gave me hands-on where there were real experts. So I was working with EMI, so the profits from the Beatles, the Beatlemania, they reinvested that into CT scanning. So
EMI,
the engineer...
EMI was the record company,
EMI
right?
was a record company.
That represented the Beatles, so they're making crazy money out of the Beatles, and they're taking that money and using it for research.
What's interesting, they were an electronics company, and in the war, they developed a lot of detection using radar technology and a lot of new electronics for detection. So that expertise gave EMI a grounding in particularly domestic products. So Thorn EMI they produced a lot of radios and things like that.
It's incredible. I just had this thought that the Beatles actually helped science.
Yes. Yeah.
In this indirect way.
Yep, they
but
financed.
the profits were financed like some crazy science out there.
So what happened, I actually worked with an engineer in EMI that got the Nobel Prize in Medicine because he invented the CAT scanner.
And he was an EMI employee.
And he was an EMI employee. What was sad about EMI is that they didn't really manage their investment very well.
A bit like Xerox, right?
Yeah, within 5 years, they went bankrupt.
Yep.
A lot of competition. And what was interesting for me was to try and get a sense of what the environment was. So people like Siemens, General Electric, they were all sort of knocking on our doors saying, well, come and look at what we're doing. And the development of the technology was very, very rapid. Now, for me, the heart of the technology was a mini computer, the things that I was doing back at uni. and I was able to understand what its limits were. It couldn't do mathematics all that well, so you had to put a coprocessor to do the array processing.
Yep.
And I understood a little bit about the architecture. And while I worked there, I actually installed CAT scanners. So that was a bit exciting. You know, I installed the first whole body CT scanner in Europe, in Denmark. So it was really good. They paid me to do all
So
this.
what year is that?
That was 1975.
Wow.
Yeah.
That's the dawn of the microcomputer age as well, with
That's right.
home computers.
But it also struck me, they picked a microcomputer I didn't really have a background in. I was trained in what was known as the PDP-11.
That's no problem for you, right? It was no problem.
Well, yeah, in some ways I began to take sides, and later on I wanted to rationalise and I tended to back a particular brand of microcomputing. Mm-hmm. While I was doing my masters, there was a mentor there, Dr. David Mee, and he made all the master's students, even though that they were working, they were coming to uni at 6:30 at night, they actually had to do wire wrapping and construct a peripheral board. And that led me on later on to these designs.
Hands-on knowledge.
He picked...
Learn by making.
Learn by doing,
And
which was
doing.
totally different from every other course in the master's program. And I was able to, for the first time, I actually learnt wire wrapping techniques and played with what was known as PIAs, like parallel interface devices and things like that, and submit those as part of my for assessment. Mm-hmm. So that actually made me, it jolted me into going to another level, because there were two competing things. One was hands-on, do something so that you can really understand it. And the other one was you go to a management role where you tended to only write about the specifications and test them. So you were a bit remote from the process. Mm-hmm. And the two of them were sort of conflicting, if you like, in my mind. Where would I go? Was it either that management approach, or could I get my hands on and do something?
So did you see a conflict between that hands-off management approach and the hands-on, more like applied approach? Was there a conflict between the two, or they were just two separate things that coexisted and collaborated with each other and just couldn't decide which one to go for?
Well, I enjoyed beginning to make stuff.
Yeah.
So, and it also happened while I was an undergraduate, they tended to use a lot of obsolete equipment. Mm-hmm. So the quality of labs at Sydney Uni were sometimes very, very good, but most of the time they were pretty bad.
Mm. That's the thing that I was shocked leaving school. The quality of the labs at school were far better than the labs that we had at university.
Well, they didn't maintain them. So we were doing things like phase lock loops using valve, mainly equipment that was using valve technology, and none of it was calibrated. Mm. And right at exactly the same time, they were beginning to introduce little circuits on integrated circuits, the 555 timer and the 556 phase lock loop.
Yep.
Now, I was the first one in the class to actually go and buy those from Babylon Electronics from the Silicon Valley and do all the lab experiments at home. So I had an oscilloscope.
Using your own equipment, right?
So I started, I was, as a full-time paid undergrad, I reinvested some of that money back into electronics and developed a lab which was better than what we had at uni.
So you really believe that you need to have the right tools as part of learning, right?
That's right.
Especially in technology.
Yep. Yeah, the fundamentals, I had a signal generator called a mini lab, and the other one was an oscilloscope, and I was soldering iron, all those sort of things. And with a bit of hands-on, I could still continue a little bit of that all the way through.
So at that point, you're still a student, aren't you?
Yeah, I was still a student when I was doing that. It became a bit difficult as a maker to do that while I was doing the masters and doing these other full-time.
Just busy time in life.
Yeah, it's quite, because I also looked after things like the nuclear medicine program for New South Wales. And what that is, nuclear medicine, I don't know if you've ever if you've heard of it, but I had to commission gamma cameras and then select the first micrcomputers in state hospitals. Mm-hmm. And that was quite interesting.
So these are scanners that you can use in order to inspect internal structures in the body, like the brain. Would that be a good candidate for the scanner?
More than just structures, they're actually biochemical structures. So while you look at an ordinary X-ray, you just get a bone structure.
Right.
This is actually able to trace through the biochemical reactions.
So you can see the tissues there, but you can also see the blood flowing through
you can see the blood, but you can also see the biochemistry
chemicals
of the liver.
Right.
So they could actually have radiopharmaceuticals which would be tagged for certain parts of the body.
Right.
And then you could photograph those processes.
To do that, you need a computer to analyze the signal that you're getting from the scanner, and that's one of the things that you had to learn and do as well.
Select the first ones, and it goes back to, well, if I could rationalize on the computer system, and it was all stuff that was more intuition rather than policy. So I selected the same computer system for all the teaching hospitals right throughout New South Wales.
Surprised that the computing systems are so decoupled from the scanners. Because you walk into a hospital today and it's a branded PC running some god-ancient version of Windows XP that's controlling, some very expensive equipment. It seems to be built, embedded into the equipment. Back then it was separate?
It was all separate.
Okay.
So I guess it was a bit of luck, because the hospitals wanted to collaborate on research, and if they could write software, then other hospitals could use that software too.
Right. So they didn't even have the software to run on it, yet they had to make it themselves.
They had packages. So there was a company called Digital Equipment Corporation, DEC. So they actually had a package called the Gamma 11, and that did most of what they wanted, but not enough for a teaching hospital. They did research on top of that.
What were these machines running? Unix?
Operating system.
There was they ran a real-time operating system called RT11.
Okay.
And it had to be real time because these signals were coming in, you had to process them. And they had a little mini version called the LSI-11 eventually, and it went into ultrasonic scanners. So besides nuclear medicine, it also went into another new field called that looked at ultrasonic imaging.
I'd like to fast forward now to when you were actually doing the teaching. Because so far you've been doing like an amazing amount of learning really quickly, diverse field, and technology and medicine and all these other things, and also diverse background. So you went government, you went to still government, but in hospitals, and so you got a very big collection of experiences. Now you become interested in academia, and you become an academic at some point in life. Can you tell us a little bit about that, and then how did you use all that experience in your own teaching style? Tell us maybe some of the techniques that you used, or the mental tools, or even actual technical tools like computers in your teaching.
Well, there was one phase just prior to that, and that is I changed government departments.
Right.
And this government department actually had a lot of worldwide expertise in microcomputers.
Which one was that?
It was the Department of Main Roads.
Main Roads, yeah.
And they invented a system called SCATS. It's called, I don't know if you've ever heard of that.
No, I haven't.
Sydney Coordinated Adaptive Traffic System.
Okay.
And it used microcomputers on every intersection, but they then linked them up in a hierarchy. So each region, the Hornsby region, would have its own mini computer, and then they had a VAX computer. So the whole of Sydney was actually part of a wide network. So we're going back to about the early 1970s, and they were a world leader.
So what does that system do?
It coordinates.
So it coordinates when the lights will go green, amber.
Well, what was interesting, Sydney...
Is that what it does?
Well, it compensated for the lack of planning in Sydney. Well, the streets used to follow the old bullet trails. And so you have terrible topography in Sydney.
Yeah.
And to compensate for that, so where there's a need, people will invent something. So we invented a coordinated traffic system that gave priority to the main flow and tried to use the image of an army platoon, so package the whole of the traffic into platoons, then synchronise them, and then make that adaptive so that if there was a change in events, the system would be able to learn that. And then, so it wasn't a time switch system.
Yeah.
It was a system based on measurement of where the traffic was, and deliberately trying to flow,
to push it through the
push
system.
them through,
Right.
and then coordinate the different platoons. Now, what was interesting about that, the whole thing was done in Sydney, and it was exported. So it was using microcomputer technology. So if you go to Hong Kong, Shanghai, almost every city in Asia, they use the technology that we developed in
Started
Sydney.
here, yeah.
And most of Australia, except Brisbane, they wanted to do their own.
Of
But
course,
what was interesting about that is that I got involved in a basic micro technology, including this ALF machine and materials testing. You could do it all yourself. So you could design your own computers.
How big was the team that developed that system back then?
For the SCAT system,
Yeah, the SCAT system.
there'd be a team of about, say, 15 people.
So it's quite a significant operation. So
Yeah, it was a significant
programmers,
operation.
engineers,
Yeah, they worked in Oxford Street. They're now, if you've heard of the Transport Management Centre in Sydney?
Yep.
Okay. The core of that is the people that developed the traffic light system.
All right.
Okay. Which is now there. There used to be in Oxford Street in Sydney, and it's now in the Transport Management Centre.
Is that now Technology Park?
In Technology Park, that's right, Australian
Redfern.
Technology Park.
ATP, yeah.
So the interesting thing was that we had hands-on, and I kept on learning about techniques, particularly from the SCAT people, and applied those, not to traffic management, but I applied their technology to building roads and selecting quality material. Yeah, so that got me interested in applying for a higher promotion, and I went to UTS as the engineering manager in the School of Electrical Engineering.
Until when?
That was 1988.
1988. And what time did you finish up at UTS?
Well, I started UTS in 1988 and stayed there about 10 years.
Okay.
Then I went back into the roads people again, to the RTA.
Before that, I'm curious, why did you decide to go to academia? Because it seems to me like you were having a lot of fun until the time. Like your projects are amazing, and like tremendously interesting. What drew you to go to academia?
Well, UTS started a brand new degree, Computer Systems Engineering, and they wanted someone with a pretty solid background in microcomputing to develop all the laboratories.
Yeah.
So they employed me as a support staff. So, I actually had to, they had to create a new position, which was the same as a senior lecturer. Very unusual for a support staff person to get that high in those days. But they had a lot of money. So the Navy were building submarines.
Yep.
And UTS taught the Navy software engineering techniques. So they were getting money from industry.
Defence money.
So Rockwell, that money was being thrown at them.
Yeah.
And my directive there, my aim was to get that money and put it into a program, but it didn't last that long. So for about 2 or 3 years, once the labs were all established, the source of finance, we were getting $100,000 a year budgets for our computer systems engineering. So I had to come up with a program with the academics that would keep students active in computer engineering. And the model there was, let's imitate industry. Let's get industrial strength things.
So that's where your background is coming in at this point.
It was different in the sense that they went for things like VLSI design tools and mentor graphics, a lot of things which really needed a team behind them, but we didn't really have many people employed to actually keep them running.
Yeah.
So it was there was a lot to learn. How could you keep a university, in a sense, connected to industry, using the same tools that they were using, but at the same time, how do you do that in an academic environment? Not easy.
Yeah, that's a different situation. I'm curious about how in the first few years in your association with UTS in that capacity, did you come in contact with, you were teaching, right? You were not just...
In the first 2 years, I was only doing a small amount of teaching.
Right.
So Noel Carmody, for example, who did VLSI and real-time systems, I helped him with some subjects. I started doing lectures in project management.
So you studied your lectures then, that's your first contact with students. Are they master students or undergraduate?
Undergrad students.
So what was your, your experience with those students coming fresh from school in an undergraduate program in engineering? What were they like back then?
It was their first time that they experienced project management, the theory of it. So UTS was a bit different because most of the students had some feel for industry, and so their appetite was already whetted. If you were to do that elsewhere, I think it'd be quite difficult. So
I was actually a UTS student right after your time. I landed in there 2002.
Okay, in where? In electrical?
Engineering.
Electrical?
So there was a program called a Bachelor's of Engineering Innovations, and so that was meant to be half business, half engineering.
Okay.
With the view of creating little entrepreneurs that would go out and make things.
Okay.
And so I did a lot of engineering subjects in building too.
Okay.
And so I got a real feel for what you left there in terms of the electrical side of things.
So UTS was very strong on project management. So I don't know if you ever came across Peter Lewis at all.
Yes.
So I assisted Peter Lewis. I moved more into the management side. All the money had dried out. Yep. And it was also, the funny thing was my involvement in maker culture dried up then. And it was partly the social context of it. Previously, I was actually working with, particularly in the roads area, working with electricians in a collaboration where they wanted to learn themselves, and we actually worked very, very cooperatively. But at UTS, there was a bit of antagonism amongst the support staff, and you couldn't actually go into their domain too much. So there's a bit of separation, and there was a lot of backstabbing with academics.
Wow.
So it was quite a tense environment. But at the same time, UTS were leaders in education innovation.
Yeah.
So they actually introduced new techniques of introducing students to engineering by discovery, by hands-on, and by also they involved the literacy side to screen all the students who had bad English.
Yeah, we had this subject called Engineering for Sustainability.
Okay.
And that sounds like a very interesting subject. It's like you look at that on the course program, it's like, oh, we're going to create solutions to help the environment and to live sustainability. No, I was writing essays on, was it John Henderson, the guy who invented the clock for navigation. And it was just essay writing the whole time. I'm going to sound very racist.
What process?
It was simply to screen out all the ESLs.
Well, I was involved in the first, in the program just before that, and it was called Engineering Practice and Engineering Discovery.
Interesting.
But the ethos behind that was totally different from what I experienced myself as an undergrad.
Yes.
Very exciting, and I became very interested in that and did a postgrad course on higher education, on the fundamentals of how adults learn. And I really liked that. That was something that I enjoyed.
Did you like teaching?
Yeah, I loved it.
So did your teaching increase over the years?
It took. So I was doing less and less in engineering management, and the academic side began to increase quite a lot.
So tell us about your the core of your teaching years at UTS. Tell us about the students. Were they practical kind of people, especially in the engineering school? Did they understand the concept of learning through making? Did they collaborate with each other and with you to build things?
A bit of both. There was one subject I got involved in called Introduction to Electrical Engineering, and I got involved in that. And that was about the students had to make hands-on.
So were they project-based learning?
Yeah. Did you do that?
I did that subject.
Oh, so I was one of the facilitators.
Okay, we had to make a data acquisition device.
Okay.
So,
did you have to did you choose to make the device?
No,
or was it an allocated topic, or
they,
did you have
They gave us the design that we had to follow. And this was all pre-Arduino.
Yeah.
Yep.
So, we're plugging in with parallel ports and what have you. It would be so much easier to do
today.
What we did back then today.
Yes, it was.
Crazy.
Now, what was interesting, all the facilitators, they weren't lecturers, they were facilitators to try and motivate and give feedback to students. They had to go and do the construction too. And so we got involved quite actively. It was team facilitation. So you break, when you were doing your subject, that subject in Introduction to Electrical Engineering, there'd be a small team of students with a facilitator.
Yes.
About 15 or so?
Yes. We had a really good facilitator. Can't remember.
Yeah, she was one of my, we worked together. And David Lowe was another one. So we actually worked together and it meant for the school, it was a very expensive resource problem for them. Because for one subject, you ended up with a team of perhaps about 5 or 6 facilitators. And it had its downside, and the downside was that it was more expensive. But from a
was it
student
worth
point,
it? In your opinion, was it worth it?
oh, definitely, yeah, because you're able to get feedback, you're able to get to know the students, and you.
What did the students get out of it?
I think with a hands-on approach and relating that back to reflective learning, they were able to learn much more rapidly than the silo approach.
Well, what do you mean by reflective learning? Just to define that.
Well, we introduced a technique where students had to spend the last 20 minutes of their session thinking about what they actually learned and whether what were the principles and what they got out of it. Then they submitted that reflection to us. So we had a conversation and we were able to talk about any issues they had in that. So if you got negative trends, you were able to sort of follow up on that.
So I can imagine the student, did you go through this, Marcus? You finish with your session, you plug in all your components together, you write your software, it works. Normally that's where you go home, right? But in your case, you didn't. You had to reflect on it. What did that do?
I cannot remember that bit, to be honest. I feel
Philip, what do you think that did to students? Like that reflection at the end of this hard session, I suppose, and you've got to think about it.
Well, it was actually meant to start a process which was going to be a bit more than that. So while you were doing it there, it was hoping that when they were sleeping at night that night, or even the next couple of days, the memory would still continue and the learning process was not just terminated at the end of the session, but would continue.
I think, isn't that the purpose of a report? So a lot of other subjects, they get you to do a project and then write a report about it.
Yep.
So the report is not really so much to show your teacher or your supervisor that you actually did the work, but it's really for you. You're writing the report so that you can remember and reflect on what you've done, especially problems that you encountered, the process of solving those problems, other issues that you found extraordinary, perhaps you note them down. But in your case, in that introduction to electrical engineering, it was more informal, right? You didn't have to write a report. You have to reflect on what you learned for the last 15 minutes of the session.
In some ways, it was driven by formal philosophy, that reflective learning and those processes, we studied the psychology behind that. So we knew about that. We also knew that a lot of the students had problems with literacy. And when they did the batch prior to you, when they were doing their thesis presentations, a lot of them couldn't even speak.
Yes.
And they couldn't write. So we had to screen for those problems in communications as early as possible.
Now, I think of my teaching career as well, because I spent 15 years in academia as well, and I know for a fact that formal report writing, especially for students whose language was not English as a first language, was always a fear. It's a big fear that they had, and all that acted negatively to that opportunity to reflect on what you learned. And I suppose by not having to write a formal document on what you learned, but to take the opportunity to reflect by discussing or thinking or explaining to your supervisor, to your friends or fellow students, it removes that fear. It makes it informal. You retain all the positive aspects of this reflection,
Yes.
remove all the negative aspects.
And what was a little bit different about that, we encouraged them to tell us how they felt about the process. So if they didn't like it, or if there was something that they didn't understand, they could actually put that in the report.
There's the opportunity.
So rather than pretending it was a completely objective scientific report, we were trying to get away from them copying. And it was their own work.
I think I lacked the self-awareness to understand that that was what was really going on back then. I just viewed it as more work,
Yes.
to be honest. Okay, interesting.
So Phil, mindful of our time, there's a couple of questions I'd like to ask, just to drill into your philosophy side of things, not so much the practical engineering aspects. In the time that you were teaching engineering at university, what were the biggest challenges that you saw students having to face in order to learn especially difficult concepts in engineering?
Well, I think there was quite a number of them. One definitely was the language. We're getting more and more students from China and from Asia, where English was their second language.
Absolutely. I had classes where I was the only white guy. Like, think about that. That's crazy. So
there was a language barrier.
There was a language barrier, and also we were getting it wasn't just for the students. We were getting a lot of lecturers that were coming from all over the place, and it was difficult for the students to understand what the lecturers were saying.
I never had that at UTS. I had it on one occasion at Sydney Uni.
Okay, yep.
Where he actually just broke out into Chinese because the rest of the class.
Well, I suppose it's the price to pay in a multicultural environment.
That's right.
Everybody's got a weird accent. But apart from those barriers, I suppose that there are things that you can do about, like if the language was not a problem and the barrier then was difficult concepts, how would you go about as a teacher? How would you go about helping a student just overcome those difficulties in understanding difficult concepts?
Well, in the communication side, we formed a liaison with other academics in other schools. So there was a group of academics that would specialise just on improving English communications.
Right.
So you'd be able to select those students, and they could be streamed into further support in language
to help them
speak
and understand better English.
Yep. Yeah. And that was more strategic. So what you wanted by the end of that, say, session, that the students would realise themselves that they had to invest extra time in learning the language.
Yeah. Well, beyond that, from my own memory as a student in engineering, almost every time there was a new concept that I had to learn, I would stumble across difficult concepts. So I know electromagnetism and all the different equations that describe it. And mentally, I wasn't ready back then when I was 20 years old to understand some of those difficult, especially mathematical concepts. And then what would I do about it? Not much. I would struggle. I would try to find another textbook, perhaps. Maybe if I was lucky, I would be able to corner one of the lecturers and they would try to explain, but usually I wouldn't be able to understand anyway. So that there was a lot of struggle there. And I think with degrees like that, in engineering, in medicine, in science in general, there are difficult concepts that students struggle with. Did you have a particular technique to help out your students who were stuck with a particular difficult concept?
I think doing it yourself, making sure some of the very busy academics really didn't get too much involved in hands-on. But if you were able to do it yourself and you knew what was going on, then the students had more confidence and they could talk to you. Whereas I noticed we had some facilitators, PhD students and others, that had difficulty understanding how a transistor worked.
Yes.
And when students were asking them, it was quite clear they were giving them the wrong advice.
So the instructors, the teachers, I should say, they were themselves having trouble understanding a concept, like how does a transistor work?
Yep.
And
Yes.
then
We had a
would ask them.
mixture. We had a mixture. Because UTS, one of the problems of UTS, it came from an advanced college of education that had a focus on learning and quality learning. Then it suddenly had to pick up research and getting money from industry. So academics were pretty busy if they had to do all those things. You couldn't do them all perfectly. And so you had some of the senior people, professors and things like that, they would perhaps ill-prepared go in, and the students, when they asked questions, it was obvious that they weren't getting the right support.
Yeah, so I was not the only one.
I do not feel that UTS better.
No,
I think UTS was a bit different from Sydney Uni too, in that the students would often rush in from work,
yes.
and they
Oh,
didn't.
absolutely. I had half an hour to get from work to UTS.
Yep.
Yes,
Well,
it was a rush.
Where at Sydney Uni, the lunchtime sessions, you would go and listen to a visiting professor from Harvard or something like that. UTS didn't have anything like that at all, nothing. And at Sydney Uni, what was more important to me wasn't the lectures, was the access to the whole university environment and joining clubs, political groups and other groups like that, and bushwalking
It's a more
clubs.
traditional academic environment at Sydney University.
It's more traditional,
Yeah.
but it also had a lot more exposure in terms of particularly politics. So the Vietnam, well, I was involved with the demonstrations against the Vietnam War on the campus, and the philosophy students, they were quite active in this. Whereas
Philosophy. UTS didn't have one.
there was a completely different environment at UTS. And to me, I thought, well, education to be more rounded, it would be good to have a little bit of that.
But
Yeah, they had the engineering society and the IT societies, but I can't remember any political societies.
Yeah. Well, there was no campus-wide participation. You tended to be in silos.
yeah, I think the tower building doesn't help either.
Yes.
Yes.
And it became a
That's the
crisis.
silos.
But they actually at one stage said, let's have no more schools. And they then said, we'll go into a matrix structure.
Okay.
And the matrix structure meant you could come out of engineering, electrical engineering, and you could go into two groups. I picked environmental engineering, and what was the other one? Professional, the area of management, not computer, just engineering management. But you could actually choose them.
Did that actually work? Because I know that the matrix organizational structure became popular in the early 2000s, and a few other universities decided to follow them, like UWS.
Yeah.
But did anything come out of it? Did things improve?
Well, I was just looking up a colleague of mine at UTS, Ravin Bagia, and I noticed that he's the deputy head of school. So they seem to have gravitated back to the school structure.
And that's how it is now.
Yeah. But it was, when I left UTS, it went to a group structure. But it was sort of interesting. I was interested in the environmental engineering, but only two people, other than the professor, bothered joining the group. So it died out.
Interesting. I think in large, I don't know, that's another thing that we can learn through experiment, but it seems like in large organizations, structures have to be clear in order for them to be rigid and successful. And the matrix system didn't seem to have that clarity to do our report now. And okay. How about we go into rapid fire questions?
Rapid fire questions.
So rapid fire questions are short questions. You can take your time to answer them. It's not a race. It's just we'll try to keep it short in order to focus the conversation. So,
Sure.
Did you want to go first, Marcus?
Sure. So, Phil, who has been the most influential in shaping the way you teach?
A person that was in direct contact with you, perhaps, or a historical person, or an author, somebody whose work influenced you as an educator.
Well, from UTS, Elizabeth Taylor, I mentioned her earlier tonight. She was a lecturer, and she
not the actor.
Not the actor. No. She was a civil engineer, and she was employed in the School of Electrical Engineering, which was a bit unusual. And she looked after the context of engineering in the wider areas, the connections between engineering and society, and putting engineering out of the laboratory in context. So it was quite...
How did that influence you?
Well, in the she was the subjects that led on to sustainability. She was the spearhead in all of that.
Okay.
So particularly the academic program. So she got groups of academics to talk to each other. So you would actually...
So she fostered collaboration and communication.
There was a
right?
collaboration, and we would also go to conventions in education where other lecturers would talk about the latest ideas.
Not in engineering, but conventions in education. How to teach better.
That's right, how to teach better. So we would go to those, and we were very innovative in the way that we were going about that.
Yeah.
And
so she influenced the way that the subjects would operate as well, like how marks would be allocated, what kind of projects the students would undertake, how assessments would run. So did you see her influence into the practical aspect of how classes and education was actually run at GTS or at the department?
Yeah, right through to making sure that the course was well documented. You had a curricula and it was still flexible, and you went in for flexible learning. So we actually have things like learning contracts. I don't know if you've ever come across those.
I did those in UTS, yes.
I think
The students had to sign the contracts, right?
And part of that was to try and take the power away from the academic and share that power with the student. So she got involved in looking at education from a different point of view. We were facilitators. We weren't allowed to be called lecturers. So in some ways our role changed. And I think it was quite exciting. This whole idea of team involvement was very, very interesting. And you did it. You didn't even know you were working hard. You actually enjoyed it.
So it sounds very much like Maker-style education. It's the team-based and mentorships instead of lectureships, and all that sounds very familiar to me. So Elizabeth Taylor, she's going to be in the notes. I've got another one. Let's say that you've got a young educator just starting out now. What advice would you give them?
It depends on their background. I think we have learning styles which are different. So while I've spent a lot of time in higher education, postgrad, undergrad, I've also spent time with people who've got disabilities.
Yep.
So it sort of depends on inclusion and what that person is capable of doing. So I'm really keen on that, because rather than keeping people isolated and they're not part of the mainstream, I think everyone's capable of fulfilling their goals as long as they've given the right guidance. Yeah. So
do you think that the educator needs to be confident to operate as a guide, perhaps, to help the students find their own goals?
I think it's different. Some students will just come in and they already know the subject. They might even know it better than you. So they're going to be in the minority, but you're going to have a whole spectrum. I don't think you should treat the whole block of students all the same.
Everybody's different.
They're all different.
There's going to be advice for the new educator that just remember everybody in front of you is a different person.
Yes.
You can't treat them all as the same and the one, right? So
and they're going to have
advice.
they're going to have their preferred method of learning.
Yeah.
Now, some are going to be good. I'll play around. I'll make my own stuff, and that'll motivate me to go and find out from the theory of why it works. But you'll have others that just prefer to learn from the textbook.
So you have to adjust to the student, not the other way around.
I think both. I think it's a conversation.
Yep.
I think
so. That both parties need to be flexible.
Yeah.
But you think that the educator has a bit more responsibility since they are the mature party in the relationship?
Well,
I teach flexibility to the student.
I think the facilitators got the advantage that they see the relevance of that, and they can give guidance where there may be too much time spent on a particular area.
Yeah.
So they can give weight to the different parts of the curricula. Yeah. So they can give guidance and support.
Right.
So, given the time, I'm going to go straight to any parting thoughts for our listeners, do's, don'ts, and things to look out when teaching technical subjects.
I think one thing is make sure the education and the learning is lifelong. And from a very early age, and I started off at 9 building stuff, start as early as you can.
Okay.
So I think that's important, and make it something that you have fun with. So while there are methods to assess the learning, there's also a process there where you can really like it. So I think that's important too, that you maintain that interest right throughout life. So while they finish the subject and they're good at it, then that shouldn't be the end of it. Now, an example of that is, I found it really difficult to find engineers that could draw, and yet in school, they only encourage drawing in the early phases of school. And I noticed that we went to the last session, and the same thing happened with coding. They were saying, let's get away from the visual side because that's the primitive side, and we'll move towards more of a syntax and a more of a line by line, a verbal description of coding. And to me, there may be people that like to do both. And I thought, well, if you're going to encourage creativity, you don't suppress something and bring in something else. You look at the blending of what people have done. So I think that maintain the skills, maintain that right throughout the learning process, rather than letting them die.
Learning never ends. As long as you're alive, you learn.
And
But
also
do it consciously, right?
and also doing the whole process. I've noticed a problem at the moment where schools perhaps go more into the coding and neglecting the mechanical side of it, or putting that together.
Certainly, we're seeing lots of schools jumping headfirst into Python. And there's, I'd say, I don't know if to call it the minority, but there's far less schools actually doing the breadboarding side of things. It's almost as if, oh, look, we've got our makey-makeys, we've got our little bits, we've ticked the boxes, and away we go.
That's not real learning, right? It's just ticking the boxes.
Well, one of the things that I was quite weak at was mechanical engineering, because I tended to concentrate on and becoming more and more specialised right through to computer systems. Whereas when I had to actually, and this is only just recently, I had to go and find out the right screws for my robot. And yet in the past I would have said to a mechanical engineer, well, what do I need? Will you do it? And yet really, if you should be involved in the whole process. One of the good things about UTS was they encouraged a style of engineering called systems engineering, and they taught that formally, whereas it didn't exist anywhere else. And what it meant was you looked at the broader holistic picture. And I think that was pretty good. But at the same time, you really need to make sure that those skills are followed through, and that the engineering that you do, you take an interest outside of your narrow discipline.
Yeah, that's the nice thing about systems engineering. It really forces you to think about outside your specialization, how things and the components that make up something interact. Great. I think we are going to leave it at this. We still have so much to ask you, especially in your experience in teaching children with disabilities. So I'd like to touch on that topic in our next chat. But for now, do you like people getting in touch with you? What's the best way if somebody wants to talk to you and ask questions about anything that we discussed? What's the best way for them to get in touch with you?
Well, probably Facebook contact.
Facebook,
I can give you the Facebook address later on.
Yes, I'm going to have that information in the show notes later. So, Philip, thank you very much for your time today. Really appreciate it.
Thank you so much.
Yeah, it was a pleasure. Thank you.
That's all for this episode. If you have any questions or suggestions, please send them to our email address, questions@stemiverse.com, and we'd be happy to answer them. Do you want us to interview someone in particular? Let us know. Visit us at stemiverse.com to get the show notes of every episode. And subscribe on iTunes by searching for the name of our podcast, Stemiverse. That is STEMIVERSE. Thanks for listening, and we'll see you next time.